In introductory physics, an atom looks like a perfect mathematical machine. Based on the Schrödinger equation, electrons reside in perfectly neat, predictable energy levels. The classic rule for how these atoms interact with light is straightforward. When an electron drops from a higher energy level to a lower one, it emits a photon. That photon appears as a single sharp color of light, a spectral line. But as lab equipment became more precise, researchers noticed a discrepancy. The measured light didn't match the perfect model. Upon closer inspection, those single emissions were actually split into a cluster of close, distinct lines. This flowchart maps out how quantum systems behave in the real world. They start with simple baseline energy levels, but physical interactions immediately shift, split, and mix those levels based on how strong the interaction is. Let's follow that first path, small corrections. To calculate these minor quantum nudges, physicists rely on a method called perturbation theory. Think of a car driving on a perfectly flat road. If a small wind starts blowing, you don't need to invent a completely new theory of motion. You start with the known path, and you calculate a tiny correction for the wind. Inside an atom, that wind takes the form of internal physical interactions that nudge the electron's energy. These small corrections produce what we call fine structure, the exact splitting of spectral lines that early researchers observed. These three effects act as the wind: the relativistic speed of the electron near a heavy nucleus, the interaction between the electron's spin and its orbit, and the quantum smearing effect known as the Darwin term. This diagram illustrates the result. Because these effects are weak compared to the main system, they only slightly shift the energy state. One primary energy level splits into a cluster of very close, highly detailed levels. Under perturbation theory, the system is altered, but its identity as a single atom remains intact. It is the same structure, just with a higher resolution of detail. But what happens when the interaction isn't a small internal tweak? What if it's a massive external force, like a second atom moving in at close range? At that proximity, the small wind becomes a hurricane. The tiny math corrections of perturbation theory break down, and a non-perturbative treatment must be used to solve the system more fully. We can see this in the hydrogen molecular ion, or H2+. Consisting of just 2 protons and 1 shared electron, it is the simplest model for understanding how atoms actually bond. When 2 atomic wave functions strongly overlap, the electron stops being local to one atom. It delocalizes, spreading its probability over the entire structure as a single shared cloud. As shown in this mathematical summary, this intense overlap replaces the individual atomic orbitals with entirely new quantum states, a lower energy bonding state and a higher energy antibonding state. These strong interactions don't just add detail to the atom, they permanently transform its architecture, turning 2 isolated particles into a stable chemical bond. Why does this distinction between weak tweaks and strong transformations matter outside of a lab? Because these 2 microscopic math regimes build our macroscopic reality. Those tiny perturbative splittings in fine structure give every element a unique fingerprint of light. This photograph shows researchers developing early atomic clocks. Modern technologies, from identifying the chemical makeup of distant stars to designing lasers and GPS navigation, rely entirely on our ability to measure these tiny perturbative tweaks. In contrast, large non-perturbative splittings determine how atoms aggregate. By sharing their electron density, 2 isolated atomic nuclei can reach a stable, lower energy state as a single combined unit, allowing atoms to stick together into the molecules we can touch. When millions of these molecular bonds scale up in a solid material, those split energy levels multiply and merge into energy bands. This is the foundation of solid-state physics, explaining the conductivity of metals and the behavior of modern semiconductors. This graphic illustrates how interaction intensity determines the outcome. Weak interactions produce the fine, detailed splitting of light seen at the top, while the strong orbital overlap seen at the bottom create the bonding states that enable matter to hold its shape.